All right, this is Mr. McMurray, and we're here talking about simple machines. Simple as in not complex, not too bright. That's a whole different kind of thing. All right, types of machines. First of all, we're going to talk about levers. All right, levers have to have three parts. They have to have a fulcrum, they have to have an effort arm, and they have to have a resistance arm. All right, and I set one down here just a second ago, and I cannot find it. There we go. Okay. All right. An example of a simple lever, actually several kinds of a lever, would be a hammer. All right, but we'll just look at this. All right, so basically if I use this to pull up a nail out of my, I suppose, hand here, but anyhow, all right, first of all, up here is the effort. I'm putting effort into the handle, so that's my effort. Right here, we're pulling the nail up out of the ground, or the board, or whatever, so that is our resistance. The fulcrum is the part that it moves around or that moves the least, and that would be right here in the center. Okay, now this one's kind of a J shape, all right? We did it more like a teeter-totter. Okay, here would be the weight you're trying to lift, say a rock or something, you're trying to pry it up. You put your effort down here. The fulcrum would be the part that moves around in the middle, so that would be there. Okay, so you have to have those three parts. An effort arm, we're putting effort onto it. The resistance arm, which is moving whatever the object is you're trying to move. And then you have to have a fulcrum that it moves around. All right. There's also different kind of fulcrums, but if you had a door opening, the fulcrum would be the hinge, because that's where it moves around, all right, and so forth. Okay, now, there are three types of levers. There are first, second, and third class levers. All right, and so let's talk about that. First of all, they're named for what is in the middle, okay? In the lever we just talked about, like a seesaw, the fulcrum is in the middle, the effort on one side, resistance on the other side. And so if the fulcrum is in the middle, F is in the middle, then it's going to be a first-class lever. Okay? Now, if you have a fulcrum at one end, let's pretend this is the wheels of a wheelbarrow, and you're going to lift it here, and the weight is going to be here in the barrel part of the wheelbarrow. All right? When you lift that weight up, okay, the resistance is in the middle, so that would be a second class lever. And if we were doing a broom, the fulcrum would be at the top up here where it's turning around. Your effort would be in the middle, and the resistance would be the bottom of the broom. Not a very good broom here, but anyhow, and that would be pushing on the ground. So if the effort is in the middle, then it would be a third class lever. So FRE, free, or FRE if you prefer. Free reminds us of what kind of lever. Fulcrum in the middle, first class. Resistance in the middle, or the weight in the middle, second class, and effort in the middle is third class. All right, now let's talk about those in a little more detail. All right, first class lever. All right, I can't write all these on here, but I'm going to have you label them. All right, this is the fulcrum. All right, it's like a seesaw, teeter-totter. This is Mr. McMurray's effort to draw a rock. Apparently, instead of the freehand, I got the polygon, and so it looks like a house that tipped over, but really this is supposed to be a rock. And this would be your effort. So this is your effort, this is your fulcrum, this is your resistance, F-R-E, E-F-R, and so fulcrum is in the middle, so it is in fact a first class lever. Now, the distance from the fulcrum to the effort is called the effort arm, or EA for short, okay? So effort arm is here. From the fulcrum to the resistance, surprise, surprise, is called the resistance arm, all right? Okay, now, if I push this down, the distance it goes down, all right, is called the effort distance. And the effort this one goes up, the distance this one goes up, is called the resistance distance, okay? So from the fulcrum to the effort is effort arm. How far up or down this goes is the effort distance, okay? From the fulcrum to the weight, or the resistance, is the resistance arm. How far up or down it goes when we use the lever is the resistance distance. That will be important to know the difference between those two. All right. Examples would be seesaw. All right. A hammer we talked about. You have the fulcrum in the middle. You have resistance here, fulcrum, and then effort. So even though it's kind of a J shape, crowbar would be the same thing. It's still going to be a first class lever. If you're prying something with a screwdriver, that would be a first class lever. Any kind of prying or pulling open, something like that, is usually going to be a first class lever. All right. Now, second class, similar. All right, except this is going to be, you have the effort here. Now you have the weight in the middle, the resistance. So if the R is in the middle, resistance, that's going to be a second class, and the fulcrum's on the end. So this is a second class lever. Okay, And this would be like a wheelbarrow. So if you put a, sorry, I can't find my little cursor. There it is. If this were a wheel, this would be the barrel part, and this would be where you pick up the handles. This would be like a wheelbarrow. All right. And so examples would be a door. A door, you have the hinge, then you have the weight of the door, and then you have the doorknob on the opposite side. Except in Mr. McMurray's room, we're having a knob on each side. Okay. And so normally we use the handle that's farthest from the hinge because that puts the resistance in the middle and makes it a second class lever. All right. Third class lever, all right, is going to be like this. Okay, this is a little different. You have a fulcrum, you have effort in the middle, and you have a weight over here. Now, would we use this to lift a big heavy rock? No. Okay. Why? Basically, the longer the effort arm is, the easier it is to do it. Okay, and on first and second class levers, you can make the effort arm longer than the resistance arm. Okay, but with a third class lever, the effort arm is always going to be shorter because it's in the middle. So the fulcrum to the effort is always going to be shorter than the fulcrum to the resistance. All right, there we go. So the resistance arm is always longer. That means it actually takes more force to lift this. Okay, but if the effort distance, say this moves a foot, this out here may move 2 or 3 feet. So you, instead of multiplying your force, which you said simple machines can multiply your force, in this case they're multiplying our distance. So we don't have to move this part very far, the force part, okay, but it makes the resistance move a bigger distance. This goes back to the sweeping, okay, fulcrum here, effort in the middle. It actually takes more force to move the broom here than it would if we just went down here and pushed the broom with our hand, okay? But when I do this, I move my hand a few inches. By the time I get down to the bottom of my broom, it moves it several feet. And if I'm sweeping, I want to get through as soon as possible because I hate sweeping. And so we're multiplying distance and we get through quicker, and so that's a good thing. But usually you're going to use it for things that don't require much force anyhow because it's going to take more force than it normally would. If you put it on a heavy object like this heavy rock here, then it's going to be even harder to lift it, and it's probably not worth it. In fact, if you open a door with the doorknob next to the hinges, you basically get the hinge, then you've got the doorknob, then you got the weight of the door. So now you've made it a third class lever. That's why it's very difficult to open Mr. McMurray's door with the doorknob closest to the hinge. All right, unless you want to show how manly you are. All right, so examples would be things like a broom, a hoe, rake, any kind of thing like that you kind of bring up like that. It's kind of a modified third class lever. Baseball bat, same thing. Effort is in the middle. This hand does the effort. The other one's more the fulcrum. And then the resistance would be where you hit the baseball. Fishing rod, same thing. Once again, all things that are not really heavy, so it doesn't matter if it takes a little more force to swing them around because you can cover more distance. All right. Now, in a lever of any kind, if I try to balance this on my finger, I can, if I get what we call torque equal on both sides. Okay? And torque is a force that causes it to rotate. If I get too far to one side, it's going to turn this direction. Okay, now it would keep turning except for it's going to fall off and gravity would kick in. Okay, so that would be torque. Okay, there's also torque on the other side. Okay, and I can theoretically get them just perfect and it would say balance, but whether actually, oh, there we go, just like that. Couldn't do it in class the other day. Anyhow, so that means the torque is equal. Now, obviously, it has to do with the weight on each side. That's why the fulcrum is way over here at the middle, so that I have more weight on this side. And this one, even though it's not very big or long, has a lot of weight. But it also has to do with the effort arm distance. Okay, so that's why if I have a short arm on this side and a heavy weight, it's equal to, well, it's actually less weight on this side, but it goes a longer distance from the fulcrum, so it will make it balance. Okay, but torque is what causes it to turn. Now, the same thing could be applied to a wheel because it turns in a circle. They talk about torque on the truck commercial and stuff, and they actually have a point. Torque is the turning force that you can put behind your wheels. Okay, so effort torque is the effort arm. So if I push on this makes it the effort arm. The force that I put on it, both its weight and my pushing down on it, times how long the effort arm is. Okay. The resistance torque, guess what? It's going to be the same thing. The resistance arm, which is short, times the resistance force, which is pretty high because the head of the hammer is very heavy. All right. Pulleys. Pulleys, you just have a rope around the pulley. and you pull on it. Pulleys do not decrease the amount of force you need if you just have one pulley, but you can pull down on the pulley and it lifts something up. So now gravity is working with you, and you can use your weight and gravity to help you apply the force instead of just having to do it all through your hands. All right. Flag poles, cranes at the end of the frame poles, window blinds, that the one that pulls it up and down. All those are examples of pulleys. All right. Wheel and axle. Key thing on a wheel and axle is you have one shaft that turns something else. Okay. Now, it can be as simple as a screwdriver. You turn the handle, and it turns the little shaft that turns the screw. It can be gears of various kinds. There's lots of different kinds of gears, so I'm not going to worry about all that right now. But same thing. I turn one shaft or wheel, and it turns the others. Okay. Can't get this going, but you get the idea. All right, you've seen gears before. So if I can turn these gears, if they're next to this gear, then I can make it turn. Okay. So I turn one gear and it makes the other shaft turn. Okay, so any of the gears and stuff like that, it's going to be the same thing. All right, so screwdriver would be an example. The old-fashioned pencil sharpener, you turn the handle and it turns the blades on the inside to sharpen it. Any kind of gears, winches, and things like that, all of those are all going to be this type. Now, another thing that we need to know about this is sorry. No, I don't know. We'll just pass on that. Okay. Anyhow, inclined plane. Inclined plane is just a ramp, forms a right angle to the ground, okay? Wheelchair ramps, they have to be longer because you go a long distance, but you don't take as much force to go up them as it would to go upstairs or something like that. You can make a real steep ramp, but it'd be so hard to push up, it would defeat the whole purpose of having a wheelchair ramp. On-off ramps, overpass on the highway would be examples, and just any kind of loading ramp or thing like that that people use to be an inclined plane. All right, a screw is an inclined plane wrapped around a post. Okay, so if you take an inclined plane like this, boom, like that. Okay, that's an inclined plane or ramp. If I wrap that around a pencil, it basically looks like the threads on a screw. If you could get a little car and ride up the screw, you could just ride those little edges and go round, round, round until you get up to the top. Okay, so it's really an inclined plane. It's just wrapped around a post. Now, if it's a tall, steep inclined plane, then it's going to have threads that are far apart. Okay, if you have a flat inclined plane like this, that's easier to go up, right? And that would have, all right, really close together threads. So basically, a screw that has a real close together threads would be really easy to use, but you're going to have to turn it a whole bunch of times to get it drilled into the wood. A screw that has wide threads is going to take more force, but you're not going to have to turn it as many times. So depending what you're putting it in and how hard it is, you can decide which one's best. All right, so you can write that down. Wide threads, more force, but you turn it less. The narrow threads, it takes less force, but you have to turn it many more times to get it in. All right, jar lids, wood screws, obviously any kind of screw. Switchbacks on a mountain, so going up the mountain straight, we just kind of go back and forth, back and forth, back and forth. That's if it's a round mountain, you could just go around and round and round just like a screw, but that switchback is kind of doing that on one side of a mountain, just going back and forth, up and down the switchback. Bolts have threads. They're going to also be a screw. All right. Wedges are just a double-sided inclined plane that come to a point. Okay. And door stops, some of them are actually inclined planes because they have a right angle and they like that and they slide under the door. But if they come together like that, then they would be. More thing, if you're splitting wood, you got this little double-sided thing you put in there, wedge. Any kind of knife, so any kind of knife blade and stuff like that, usually scissors are going to be either an inclined plane or a wedge. Okay, so point comes together on both sides, slant in, then that would be considered a wedge. So very similar to an inclined plane, but slightly different. All right, all these simple machines, though, could be put into two groups, either a lever or an inclined plane. Okay, if you have a pulley, a wheel pulley, it has a thing in the middle that it turns around. Okay, well, if we drew a line through the pulley, we could say, hey,
That's